Future value of an annuity. So let's take a look at the definition of an annuity. An annuity is a series of equal payments or withdrawals made at equal intervals of time. If the payment or withdrawals are made at the end of each interval, the annuity is called an ordinary annuity. We're only going to be focusing on ordinary annuities in this unit, but what I want you to mainly focus on is how to recognize that a problem is looking at an annuity. And the way you can tell is by looking for keywords that say something along the lines of an equal payment or withdrawal, or equal intervals of time where the money is being paid or withdrawn. Okay, so there are two types of annuities. One type is called the future value of an ordinary annuity, and the other one is a present value of an ordinary annuity. And the real difference between them is whether you are saving for the future or if you presently have the money and you are withdrawing it or paying towards it. Okay, so for a future value of an annuity, which is what our focus is going to be on today, what you're doing is you are making regular payments or deposits towards the future so that you have this huge lump sum of money at the end of your investment period. Okay, so money is being put in. Examples of this would be if you are trying to save for a car or for university. So oftentimes it's very difficult to try to save one lump sum and then to try to invest that, which is sort of what you see in compound interest. But in an annuity, what you're doing is you are making small payments, so saving $100 bi-weekly, or saving $50 every week, those kinds of things. Those are examples of ways that you can save easily so that you have a huge lump sum of money in the future and you can use that towards a payment for a car or a payment for your tuition for university. Okay, so that's a future value of an annuity. This is the one that we're going to be focusing on in today's lesson. Now, just to touch on present value of an annuity, what that means is you already have this huge lump sum of money right now, and what you're doing is you're depositing it into an account and you're going to slowly take out money from there in regular intervals. So whether you take out $500 a month or whether you take out $5,000 a year for your tuition, for example, money is going to be taking out of this large sum of money that you already have. Okay, so in present value of an annuity, you have the money right now, you have that huge lump sum of money right now, and you are taking money out of it, so this lump sum of money starts to decrease over time. Okay, whereas in future value of an annuity, the lump sum that you're trying to create increases over time. Okay, so in present value of an annuity, money is being taken out. So some examples are loan payments. So for example, if you have a $50,000 loan and you put in $1,000 a month every month, then what's going to happen is that the amount that you owe starts to decrease. So you owe the money right now, you're paying towards it, and the amount that you owe is starting to decrease over time. Okay, so that lump sum is going to decrease over time. Another example is a lottery winning. So let's say you win $100,000, and so what you would probably do is try to use a small amount of it each week or every other week. And so again, you have the money right now and you're making small withdrawals from the account. Okay, so key thing to remember, regardless of what type of annuity you're looking at, is that annuities always have payments or withdrawals at regular intervals. Okay, that's how you're looking for an annuity. Okay, so for both of the annuities, there's a formula that you can use to help you determine the future value of the annuity, so the future value of the investment, so the large lump sum that you're looking for. And so we're going to look at the formula for future value of an annuity. In the next lesson, you'll see the formula for the present value of an annuity. So for future value of an annuity, just to summarize some of the things that you need to know, this is a formula for the future value of an annuity. Sometimes you'll see the letter A here. Sometimes in some textbooks they say FV, future value. And what this is equal to is R multiplied with, in the numerator we have 1 plus I to the exponent n minus 1, and in the denominator we have I. So what do each of these variables represent? A is the accumulated amount, so that's the amount that you're going to have at the end. So as you put money into an account, A would be the lump sum that you are left with at the end. R is a regular payment, so this is the amount that you're paying each week or each month or each day, depending on what kind of annuity you're looking at. I is the interest rate per compounding period as a decimal. So it's the way you would calculate it is R, which is your interest rate, divided by the number of times interest is compounded per year. So if interest is compounded 12 times a year, if you're looking at it monthly, then you would take the interest rate and divide it by 12. And that'll give you the interest rate every month. Okay, so that's what it means by interest rate per compounding period. So it would either be the interest rate per month, interest rate per week, interest rate every other week. That's the kind of thing you're looking at there. And then finally, N is a number of compounding periods. It's a number of times that you're going to earn interest. And so N is the number of times interest is compounded per year. So if it's monthly, it would be 12 times the amount of time in years, or the number of times in years that you're going to earn interest. So let's say you're investing for 7 years. The number of times compounded per year, if you're looking at it monthly, would be 12, and then 12 multiplied by the number of years would be 12 times 7, which is 84. So that's just an example. Little note to remember, the compounding interval must match the payment interval. So if you're paying on a monthly basis, then your compounding period should also be monthly as well. So if interest is compounded monthly, payments must be made monthly. If interest is compounded weekly, payments must also be made weekly. So it has to be the same. So let's look at a couple of examples. So here's our first one. It says Navneet is saving money from her part-time job. She deposits $200 at the end of every month into a savings account which pays 6% per annum compounded monthly. Navneet would like to know what her savings would be in 1 year. Okay, so let's take a look at some of the information here. First of all, how can we recognize that this is going to be an example of an annuity and not compound interest? Okay, so the key word that I read while I was going through this is that she is saving at the end of every month. So the fact that she's making regular payments, so she's making regular payments into an account, that tells me that this is an annuity problem. Okay, so what I know is that she's making $200 deposits at the end of every month into a savings account which pays 6% per annum compounded monthly. Notice that her payment periods, which are in months, is the same as her compounding period, which is also in months. Okay, and so what we want to know is how much she's going to have at the end, or in 1 year. So we want to know the accumulated amount at the end of 1 year. So what I'll start by doing is writing the formula for future value. So I have A equals R times 1 plus I to the exponent n minus 1 all over I, and A equals. Okay, so let's figure out some of the numbers, or some of the variables that we know. First of all, we know that our regular payments are 200, so that's R. We need to look for her interest rate per compounding period, so it's 6% per annum, but it's compounded monthly. So I'm going to divide that by 12, and I get her interest rate as 0.005. So what that means is she's getting 0.5% on a monthly basis. And then the number of compounding periods, well, she's getting interest 12 times a year because she's it's compounded monthly, and we only want to know how much she's going to have at the end of 1 year, so that's going to be 12 times. So she's going to get interest 12 times over that span, over a span of a year. So let's plug in our numbers, and then we're just going to evaluate from there. So 1 plus I would be 1.005, and our exponent is going to be 12 minus 1 all over I. Okay, and because I have all the values here, what I'm going to do is actually do the entire calculation in one step, just because my answer would be more accurate. And I just noticed that I didn't fill in the denominator here. So this should be 0.005. Here we go. So now we can calculate this, and I'll start by doing the exponent part first, and I'm going to simplify the numerator part and then divide the denominator and then multiply by 200. So I'm basically going to use the order of operations that I see there. So 1.005 to the exponent 12 equals minus 1. So that's the numerator all done. I'm going to divide it by the denominator and then finally multiply it by 200. And so I get $2,467.11 approximately, and this is an approximate answer. And this answer sort of makes sense because the amount that she will have invested is $200 each month for 12 months. So the amount she actually invested, and I'll just do this on the side, is $200 a month for 12 months. So that's how many times she put money in. So that actually means she only put into her account $2,400. And so if you actually compare how much she's going to have at the end of the year versus how much she actually put into her account, she's actually going to have a little bit more money, because that $67.11 is the interest that she earned over. Tranvir plans to buy a house 4 years from now. To save for the $30,000 down payment, he decides to make equal monthly deposits at the end of each month in a savings account that pays 5.5% per annum, compounded monthly. Determine what Tranvir's regular deposit should be in order for him to make the down payment immediately after his last deposit. Okay, how do we know this is not compound interest and instead it's an annuity? Well, let's take a look at some of the key words here. He is making equal monthly deposits. So that means he's saving on a monthly basis. And so this is regular payments at regular intervals. So that's how I know that this is going to be an annuity. How do I know it's a future value of an annuity? Well, right now he's depositing money so that he has $30,000 by the end of 4 years. Okay? And so he's making these regular deposits, which is what I don't actually know the value of. So I know this is a future value of an annuity problem, so I'll start with the formula again. But the problem in this case is I'm not actually solving for A, I'm actually solving for R. So what I'll do is I'm going to multiply both sides of the equation by I, and then divide both sides of the equation by 1 plus I to exponent n minus 1, and that'll help me isolate R. So if I multiply both sides by I get AI equals R times 1 plus I to the exponent n minus 1, so that gets rid of the denominator for me. And then finally I want to get rid of this chunk here, so I'm going to divide both sides by that, and I get, just move it over a little bit so I have more space, R is equal to A times I divided by 1 plus I to the exponent n minus 1. Now it's a matter of plugging in my numbers and solving for R. So let's see what information I'm given. I know that A is equal to 30,000, and I know that I is equal to 0.055, so 5.5% per annum, but it's compounded monthly. Again, notice that the compounding period and the payment period is the same. So I'll need to divide that by 12. And so I get 0.00458, and then the 3 is repeating. And then the number of compounding periods, well, he's depositing money 12 times a year, and he's doing this for 4 years. So we get 48. And if I plug in the numbers into the formula here, excuse me. I can calculate all of this in one step again. So I've just plugged in the numbers and I'm just going to solve for R. So in the numerator I have 30,000 times 0.00458. I'm going to try to put as many 3's as I can so that my answer is as accurate as we can get it. And that's the numerator, divided by, so in the denominator I have to put brackets since there's several things going on here. And I have 1.004583333 to the exponent 48, and then subtract 1, closing bracket, and then that's the denominator value, and then equals. Okay, so I got about $560. Oops, can't see that. And 19 cents. Okay, so therefore Tranvir must deposit $560.19 monthly.